Hello everyone and welcome to our tutorial on artificial intelligence. So in this session we'll be learning some more mathematical operations as well as some more operations on the images, that is we'll be working with OpenCV library. So in the previous sessions we just learned about some basic operations of splitting, and we did some basic mathematical operations like adding and subtracting. So today what we'll be doing is we'll be using a simple technique, that is a resizing of image technique. So resizing of image is very important because we need to resize our image in different applications. So there are some like advantages as well as disadvantages of resizing an image. First and foremost, the main reason why we resize the image is for our compression. So whenever you are using some application or whenever you are trying to build an application which takes in images, so the main thing is the image should not take up too much size. So the image cannot take up 40 MB or 50 MB of data. So that is a problem in real life scenario where you're trying to upload a photo to your passport application or any other application like a college admission application. So the server is designed in such a way that it can take in a lot of information about the student. So there are millions of students there, so each and every student's information must be taken. So the main problem is if the image is like too large, then the space taken by each and every person is like different. So what they try to do is they try to resize it to a particular size so that it fits in the application properly, as well as the amount of space that is taken by this particular image is very less. So very important, the resizing operation is helpful for a lot of purposes, including application purposes as well as for basic image processing. So if you're taking an image and if you want to resize the image because it is too large or too small, so then you can use this resizing operation. So how is this resizing operation happening in a mathematical way? We'll try to understand. So the first scenario is like this. So in a mathematical perspective, we can try to understand. So we have a 4x4 image. So what is a 4x4 image? The total, okay, this is not a 4x4 image. It is a 2x2 image. Sorry, this is not a 4x4 image. It is 2x2 because it has only 2 rows and 2 columns. So it is a 2x2 image here. So we are taking in a 2x2 image and we are trying it to resize it to a bigger image. Okay, so what is the bigger size of the image? It is a 4x4 image. So because there are 4 rows and 4 columns, so the output is like a 4x4 image, but the input is just a 2x2 image. So what will we do right now to resize this image is a simple question. So there are hundreds of methods of resizing using lot of mathematical operations. So you can either make your smaller image bigger or bigger image smaller. So what we are trying to do here is called as an enlarging operation. So enlarging is telling you you need to increase the original size of the image to a greater size. So increasing the size of the image than the original size is called enlarging. So what we are trying to do is we are trying to enlarge this 2x2 image into a 4x4 image. So how will I do this 2x2 enlarging into a 4x4? It is pretty simple. So as you can see here, there is one pixel P1. So pixel P1 will have a quantity that is 255, 220 and a 10. So this is the quantity, that is nothing but a RGB value. So what I will try to do is the first 4 pixel I'll use the same thing. So I will use the same P1 pixel. So whatever P1 pixel is there here, the same values of RGB I will try to place it here. Okay, so now first 4 is sorted. So similarly the second one is similar. I will use P2 here. So P2 is sorted. Now all the next 4 will be P2. So similarly, I have my P3, that is pixel 3. So P3 will take its place here. So the next 4 pixels, P3 is taking its place. So similarly, you have your P4. P4 is also taking its place. So now what you are trying to do is you are taking in the values here. So that is nothing but the P1. So then you are using this pixel to cover up the other images. So when your image is smaller or the original image is smaller, so if you want to resize or enlarge the other pixel, what you are trying to do is you are adding the same pixel in the other empty pixel. So if you want to do a 4x4 out of a 2x2, you are multiplying the number of, or you are increasing the same pixel so that it forms a bigger image. So that is what we are trying to do. So we are just scaling the pixel values to make it look like a bigger image. So this is the enlarging operation. So if you want to do the same operation, that is nothing but a shrinking operation. So whenever you want to convert a 4x4 image to a 2x2 image, it is the same operation. So if you have the main thing is you will not have P1 here. What you will try to do is you will try to take a mean or average of the values here. So then you will try to add this into the pixel P1. So the reverse operation you are trying to do. So what a reverse operation you are trying to do is pretty simple. So you have this pixel. So now if you are trying to do the reverse operation, so if you are trying to enlarge an image, it is simple. So you have P1, P2, P3 and P4. So 2x2 to 4x4. That is replicate the value of P1 in the other 4, that is nothing but our array, so it has become bigger. So in P2 also replicate it, so we have the bigger image being formed. So if you want to do the same thing in a reverse operation, what we'll try to do is pretty simple. So here we can see the example. So what we are trying to do is we have a 16 pixel image. So each pixel will have both R, G and B. So that is represented by 0 to 255. So now what we are trying to do is we are trying to convert this into a 2x2 image. So this is nothing but shrinking operation that we are trying to do. So we are converting 4x4 to a 2x2. That is the reverse operation. So what we will try to do now is pretty simple. So we can take a mean or median of these 4 values. So you have these 4 values. So you can take a mean or median of these 4 values and you can try to actually take in this mean or median of the four values and try to map it to this particular pixel P1. So similarly, you can take a mean and median of these 4 and map it to P2. Similarly, these 4 mean or median, map it to P3 and P4. There are hundreds of methods to actually resize an image, whether you want to make it small or large. So there are hundreds of mathematical functions that you could use to actually resize the image, that is increasing or decreasing its size, but you need to know what is actually happening. So if you want to convert a smaller image to bigger image, you take that particular pixel and you will add it to the other like empty pixel to make it a bigger image. So if you want to convert a bigger image to a smaller image, you will combine some certain pixels. So you will take some average value and you will try to put it there so that the image is shrinked, or it is retaining the properties but you are decreasing the size. So this is the whole mathematics that is involved in resizing the image or decreasing its size or increasing its size. So we'll try to actually code something using that. So what we'll try to do is we'll try to code using our Python. So we'll try to see an example right now. So we'll use this import cv2 function to import the OpenCV library. So now similarly it is very simple. So image is equal to cv2.resize. Okay, cv2.resize is the function, but we should read the image first. So cv2.im read. So what you need to do, you need to read the image. Which image shall I take now? Okay, I'll take the leaf image. One important thing you need to understand is every image will have its size mentioned. To see the image size, it is pretty simple. Right click on the image, go to properties. So in properties, you will have something called as details. So in details, you can see that my image is of 2048,1024. So 2048,1024 is the pixel size. So it is width is 2048 pixels and the height is 1024 pixels. So 2048,1024 is the total width and height of my image. So it will be given in properties. So if you go to details there, so then you can see how you can find out the image width and height of the image. So that is found out. So you can see this is the leaf image that we'll be using. So 2048 is the width, 1024 is the height. So 2048 and 1024 is the original thing. So now I want to reduce it to some other quantity. Okay. So what I will try to do is I will try to read this image. So leaf.jpg, I'll try to read this image. So if I have read this image properly, what I will try to do is I will try to show the image. That is nothing but cv2.im show. I need to mention the window name. So leaf is the window name. So I need to mention the variable which I am storing the leaf image. So the variable name is image. So now if I try to run this code, so it should display me the leaf. So right now you can see the leaf here, so leaf is properly displayed. But you can see that the size of leaf is very large, so it is quite irritating for me to just resize, watch it directly. So I want to resize this image. So how do I resize it? It is pretty simple. I have a function that is mathematical function, but I will use a variable here. So I will use a variable called as resize underscore image as my variable. So I want to resize it. How will I resize? cv2.resize is the function to resize. Okay, so this is the function. What I want to resize now? Which is the image that I want to resize? That is the variable image which stores the leaf.jpg file. Now the next thing is, if I want to decrease the pixel size. So if I want to decrease the pixel size, how much do I want to decrease my pixel size? So since I have seen my original image is nothing but, if I go to properties, I can see that the original image is nothing but my 2048 by 1024. So if you divide 2048 by 2, it will be again 1024. So if you want to divide by 1024, it is 512. So 1024 by 512 will try to resize it. That is half of the size. So 1024 comma 512 is the size that I want to resize this particular image. Okay, now what I will try to do is I will close this. So this is the pixel size that I want to use while resizing the images. So I am trying to resize the images 1024 comma 512. So this is the image which I am trying to resize. Okay, so now the resized image will be stored in resize underscore image. So we have given the image and we have told the dimensions to which it needs to resize. Now if I want to show that image, it is pretty simple. cv2.im show. So I will name the window as nothing but leaf resize. So this is fine, anything I can give the name. So the variable is resize underscore image. So this is the variable that I am trying to give it. So if I want to see the image, see now the image is resized. So this is how you perform the resizing operations. So if you want to perform the resizing operations, so you can just see how actually the image is getting resized. But if you want to save it, what will you do? If you want to save it, it is pretty simple. You should use cv2.imwrite. So cv2.imwrite, what you want to save? You want to save this resize underscore jpeg. Sorry, resize underscore image is a variable. You want to save it as a jpeg file. So how will you save it? I will save it as resize.jpg. So you need to mention which variable you need to actually store it as an image and the name that you want to give it to the image. So if you try to run this, okay, so one thing here. So one thing I made a mistake, it is the reverse. So I need to mention the name of the file first, then the variable which I want to store, resize underscore image. So this will work. Yes, now this image is saved. So I can go back to my directory and I can go back here. So this I can go to properties to check whether it has been resized or not. Go to properties, go to details. So details, it is showing that it is 1024 by 512. Yes, I can tell that this is the resized image that I am trying to do. So what I have done is I have decreased my original size of the image. So that is what I have done. So what we'll try to do is we'll try to increase this particular image. So if you want to increase this particular size of the image, you can use this. So I'm using another example of RGB. So it is 216 by 214. So 216 by 214, we'll take in a vague size now. So we'll not do exactly half or double of it. So we'll take in around 600 by 600. So we'll try to resize it by 600 by 600. So we'll just open the program again. So simple thing. So instead of leaf.png, I will take the other image. rgb.png is my image. Okay. So what I am trying to do is I will try to resize a smaller image to a bigger one. So I will choose it as a 600 by 600. So anything you can choose. So instead of this, what I will try to do is I will put it as RGB. So that is the image. So if I want to resize this and I want to save it as some other file name, so you can even convert. So JPEG can be stored as PNG also. That is also not a problem. So file format can be changed while saving. So you are actually converting the image. So I will name it as res.png. So this is done. So what I did was I took a smaller image that is nothing but this RGB image, which is of 216 by 214 size. Now I am trying to convert it into a bigger size by using the resize function. So I am using image 600,600. So I am actually expanding smaller image. I am trying to convert it into a bigger image. So I have the cv2.im show that will show this resized image. So cv2.im, right? It is like saving this as res.png and it is resizing. It is using the variable resize.img. So now you can see that the image which was small, it has turned out to be big, which has become 600,600. So it has actually increased the size from 200, 214, 216 to 600,600. So this is the res.png file. So you can go to properties now. So then in the details you can check. So it has become 600 by 600. So that is how you can resize your images into smaller or a bigger kind of image. So this is the resize operation that is present in OpenCV. Yeah, so one more thing I needed to talk about this resizing is, so when you're trying to resize some image, so there is some factor called as interpolation factor. So what do you mean by interpolation factor and how it is going to help you is pretty simple. So in generic terms, you know that interpolation is nothing but when you have a graph and you have a line. So if you want to extend the line, so extending the line is called interpolation. So when you want to extend it towards your x-axis or towards your y-axis, so extending is called as interpolation. So what interpolation is happening is whenever you are trying to increase your pixels, that is like from a small image to bigger image, or decrease your pixels from bigger image to small image, there are a lot of mathematical operations being involved. So you can choose any of some important mathematical operations. So the mathematical operations that we have is something called as area is one. Then we have linear. Then we have cubic. So okay, area, linear, and cubic. Okay, these are the three things we have. So what we will try to do is we can use any of these three interpolation factors. So these are the three interpolation factors that are available. So what is interpolation factor? So according to these interpolation factors, there will be some mathematical relation or operation that is being involved. So it is like, we don't want to get into too much of mathematical operations that are being involved, that are used for interpolation, but we can try them out for seeking any difference. So if you want to try them out, it is pretty simple. So you can try out using interpolation. So interpolation is equal to cv2.inter underscore, you have three things, that is area. There are more than three things, but generally we use three things. So you can't make out anything as such. So if you want to resize, so this is one interpolation factor that is being involved to resize our image from a smaller to a bigger pixel. So this is done. So this is called as area. So area, what do you mean by area? Area is nothing but according to the area it is going to interpolate. So what is the base size? It is 200 cross 200. So increased size is 600 cross 600. So the area of pixels to be increased is around 400 pixels. So according to 400 pixel area, so it is interpolating or it is increasing the pixel. So mathematical operation is done according to the area. So this is one part. So then we have something called as linear. So you can check, you can try out linear interpolation. So in linear interpolation also we cannot make any major changes because it is the same thing. So it is increasing linearly. So there is a linear expression being involved on how to increase the size of the pixel. So this is one linear operation. So then we have cubic. So cubic is nothing but it will take place in the form of 2 cross 2 or 4 cross 4 cubes. So increasing the size is happening in the form of 2 cross 2 or 4 cross 4 cubes. Again, you are not able to see any much changes because these are all the what we call them as nothing but our basic manipulation or nothing but our adjustment factor. So if you are not able to make some adjustments or if the image is unclear, so I can use these interpolation factors to make them more clear. So they are not generally used, but better to have an idea of them when trying to use this. It is basically telling you that how to increase or decrease the size of the image. While decreasing or increasing the size, it is using some mathematical expression. So if you're increasing from 2 cross to 4 cross 4, the area that needs to be added, or the area in which new pixels or pixels need to be added is 2 cross 2. So how do I add that using a mathematical operation? So those mathematical operations are described under this area, linear and cubic. By default, it is linear. If you don't mention also, it will take place in a linear manner. But if you want to change it to area or cubic, so cubic, everything will be happening in terms of cubes. That is either 2 cross 2, 4 cross 4 cubes. So even number of pixels, rows of pixels and rows and columns of pixels will be taken to do some operation. Area is nothing but according to the area it will do some decreasing or increasing, how the pixel is getting arranged or how the pixel is getting altered. So that is done using cubic. So this is one of the basic manipulation that you can do with your resizing image, but you don't need to do it. You can just use your pixel size and you can resize your image. So this is a simple technique to resize your images in OpenCV. Okay, so the next topic that we'll be dealing with is called as dilation and erosion operations. So whatever we did till now are all just increasing the decreasing or sizing of the pixels, or we just did some basic operations where we manipulated some pixel information and we were able to get some data. So the process that we'll be doing today is called dilation or erosion. So the process that is being done is called as morphological image processing. So what is this morphological image processing, or how is it being done, is pretty important to understand. So whenever we hear the term about morphology, so morphology is meaning that you're doing something or you're changing the structure completely. So if you have morphology of a human body, so what you're trying to do is you're dealing with the structure of the human body, where if you're processing or changing it, so you're entirely changing the structure of some particular object. So that is called as morphological processing or morphological changing. So what we'll be trying to do is we'll do two operations. One is called as dilation and the other one is called as erosion. So we'll start with erosion first. So what is meant by erosion, or how erosion actually looks, we'll try to understand. So you can see from this example, it is pretty clear. So erosion is similar to your soil erosion. So what happens in erosion? So erosion is a property, or erosion is a principle where some material gets eroded or some data gets eroded, or any physical object is getting removed from a particular object. So you have a stone, or you have some chunk of soil. So due to rain, the chunk of soil is getting eroded. That is nothing but a part of soil is getting lost, and you are losing out on the matter or the physical object. So that is what is called as erosion. So the concept is similar to your soil erosion. What you are trying to do is you are trying to remove some data out or remove some information out of the image. So how we are trying to remove some information out of the image is by using this particular example. But before that, why do we need to do erosion? So if I have my character A like this, so why do I need to get my character, that is nothing but get my letter eroded, or why do you need this operation is the next question. So the question, the answer here is pretty simple. So I have a particular squared image here. So I have a square or rectangular shaped image. So in this rectangular shaped image, what I'm trying to do is I am trying to have a small dot or some disturbance here. So my image is a pure white rectangular image, but I am trying to have a dot here. So what happens is, if I want to remove this dot, either I should manually go looking for this particular dot and remove it, or I can do some erosion operations which perform the operation to this entire image. So how is this erosion operation being conducted is the second question. But what is the use of erosion is pretty simple. So it will see the surrounding pixel. So there is some variation. So it is trying to remove it or it is trying to erase it. So erosion is helping you remove impurities out of the image. If you have small dots, small circles and impurities, you can remove this. Best example of erosion is when you're trying to remove pimples from your faces. So that is the best example. Using any computer software, if you're trying to remove some colored marks on your faces, so you're just taking a tool and you're trying to erase something. So what is that actually doing is it is doing an erosion. So erosion is nothing but it is trying to mask a particular background color with the help from the total different or complex pixel that is there. So if there is some difference, so for example, black dot is a difference in this entire image because the entire image is white. So if I keep a black dot, it is a disturbance or a difference in this entire image. So that is why this is considered as some disturbance. So if you want to remove that, erosion helps you do it. So this is how it is happening. The next question is how actually erosion is happening. And how actually morphological image processing happens is the next question. So how morphological image processing happens is, so this is the way how morphological image processing happens. So this is called a filter or a kernel. So the small colored or the small image, the green colored image which you are able to see here, this is called a kernel. So what happens is, as I told you, if I have a small black colored dot in my image, so how am I going to remove that black colored dot? If I'm doing it manually, I can tell that there is a difference. But if I'm trying to do it using a computer, what this particular filter does is, it goes through the entire length and breadth of the image. It is like a smaller part when compared to the image. Image is like a bigger part, bigger chunk. It will be like 100 cross 100 pixels or 1000 cross 1000 pixels. So when you're trying to like erode something or remove some impurities, what you're trying to do is you're trying to go step by step. So you're going, this particular small filter will like run through this entire image. So after running through this entire image, it is going to search for impurities. So if there are impurities being found, so then it is going to replace it with the surrounding surrounding data. Hence you are getting a clean data. So that is how your erosion is happening. So all morphological image processing operations, so whenever I tell morphological, the whole image is getting altered, the whole structure of the image is getting altered. So how am I doing this? So like this, we have something called as a filter or a kernel. Filter or kernel is nothing but a smaller part of the image or a small set of pixels that is going to run through the entire image and perform some operations. So it is going to cover each and every pixel. It is not going to miss a single pixel also. So that is how this morphological image processing is done. So even erosion is done in the same way. So we are going to send a small pixel to run through the entire length and breadth of the image. There, if it finds out any impurities, then it is going to remove those impurities. So that is what it is going to do. Okay, so now learning about erosion, we'll come to the part of erosion now. So looking at this particular example, so what we can realize is, the kernel which we choose for erosion is nothing but a 1, 1, 1 kernel, or what we call it is the kernel which is filled with 1. So what is 1 meaning is, so 1 is meaning that it is a black, almost a black colored pixel, close to a black colored pixel. So this set of, it is, now I'm just choosing a 2 cross 2 image, so it can be 3 cross 3, 10 cross 10 or 20 cross 20. But the whole, what is the thing that we need to understand is how it is actually working. So the kernel that we'll be taking for erosion is a 1 cross 1 kernel, or what we call this a set of ones. So the kernel is a set of ones. Set of ones meaning that all the data, all the pixel information inside it will be 1. So it is just a entire black colored image, because we know that 0 is close to black, 255 is close to 1. Now what we'll try to do is, we'll try to work on the image. So if I want to try to do erosions on this image, how it is happening. Okay. If I want to try to do erosion on this image, how it happens is, this 1, 1, this particular kernel will go through the entire image. So it will go through here first, then it will go through here. So it is going to cover the entire image and try to go through the entire image. So that is the operation it does. So it is going through entire rows and column of the images. How it is happening is, if a particular pixel, so if I'll try to compare a particular pixel, so if my particular pixel is around like 2, 3 or 4, for example, I have a particular pixel here which is around, which is of a lesser quantity. For example, it will be around 2, okay, this will be 2, so this will be around, so the pixel color is 2 here, so okay, let the pixel color be 2, here it will be 23. Okay, so now what happens is, it goes through this particular set of pixels. So my whole kernel is going through this 4 pixels. Now 1, 1, 1, 1, it is trying to go. Since the values are lesser, there is no abrupt change in the intensities of the image. It is not going to do anything. It will pass. So then it will pass to here. So here also there may be some values. If it is not intensive it will pass. Now what it is trying to do is, it is trying to check for variation in the intensity. So it is trying to go through the entire image and trying to check for the variation in the intensities. But if you can see the example of the image that is that I have given here, the practical aspect of erosion is it has just removed the background. So it has just removed the edges, but the whole A is still visible to you. So that is what is erosion. So actual concept of erosion is pretty simple. So when you have this kernel that is passing through the entire image, it is checking for the variation in the intensity. So suppose if the intensities are very smaller, it doesn't change anything. But if the intensities is large, so I will compare this. So the intensity is large here. So what it is trying to do is, it is coming to the pixel here, and then it is trying that this intensity is large, so it removes this particular pixel. So this 255 is getting removed. Why this 255 is getting removed is, there is a variation in the particular pixel information. But here also there is a 255. Here it is not going to change that, because there is a it always covers the first line first. So it is taking the first leftmost element it will try to cover, then it will move on and it will try to change. There are different methods. It need not be a square pixel also. Sometimes we might use a plus symbol like this. So we might have a kernel like this. So like this, this kernel will go through the entire image and then it will try to remove. So here the kernel will remove only this center part. But in case of a square kind of kernel, it is removing the left topmost part. So it is removing this 255. And this, it is replacing it with a lesser value, because the surrounding, the next surrounding values, like this value might be 23 or this value might be 34. So the next surrounding value is somewhere close to 23 or 34. It will replace it and it will replace it with 23. Or it will take a mean or something, it will replace with 30 or something. So this is getting replaced. So very important operation. What it is trying to do is, this kernel will try to go through all, like it will try to go through all the pixel. Since our kernel is a 2x2 kernel, it will come here first. So here there is variation of intensity, so it will remove it and replace it with a lesser value. But again it will come here, so here it is a small intensity, it will neglect it. But why isn't it removing these large values of intensities is, the size of the kernel is same as the large values of intensity. So this is the example. So this size of the kernel is the same as the intensity value. So what it is doing is, since all the information is of high intensity, it is not removing. Only if the information is of invariant intensity like this. So only if the one of the pixel is having more intensity, the rest of the pixels is having the same intensity, it is going to like remove that and replace it with the smaller value. If all the values inside a particular, like inside those 4 pixels is same, then it is not going to change it. So that is why I have got this. So at the corners you will have white and black pixels. So notice this. At the corners you are having white and black pixels. So you can notice this. Only at these corners it is trying to remove, because there are more white and black pixels here. So how it is doing is, when you try to zoom in more and more, you can see here. Okay, you can try to see here. At these corners, there is variation. For example, at these corners, there is variation of the data, that is, you have difference between pixels. That is, white is 255, black is 0. So there is difference between the pixels. So it is trying to replace it with the surrounding pixel. So here it is got removed. But once the kernel comes here, so I will take an example of a small kernel. So kernel is this. Once the kernel comes inside this black part, since all the pixel is surrounded by black, it is not going to remove it. Only at the point that is here, it is finding out that these points intensity is like changing when compared to this. So it is removing all these edges. So it is removing the edges and it is making the whole image which was looking like this, and it is eroding some part of the image. Why? Because it saw that the surrounding pixels are much more lighter, much more lighter intensity, or have like close to 255 value, but black is having close to 0 value. That is why it tried to remove those edges. But once the filter comes inside the particular black portion, so all the pixels are like black intensity value, so it is not going to remove it. Okay, that is what it is doing. Again when it comes here, since the surrounding pixels are white, since the edges are black, it is going to replace this edge pixels with the surrounding pixel. So that is what is erosion operation doing. So erosion is basically removing some particular data. So the best example that I would try to show today is I want to erode this particular image. So I have this black image, I have this hexagon here. So this hexagon is not needed for me. I need a complete black image. So I want to erode this hexagon in some way. So we'll try doing that, but we'll start with the programming now since you understood how erosion is happening. So how to do this erosion is pretty simple. So we'll import OpenCV2. So that is our library. But to create this kernel, so what is kernel? This 1,1,1 is the kernel that we are trying to use. So this is the kernel that we are trying to use. To create this kernel, what we are trying to do is we need to generate ones. So we need to have some amount of ones to generate this kernel. So the kernel that we are using for erosion, as well as there is another process called dilation, will be always a set of ones. That is, all the pixel intensities will be 1, 1, 1, 1. So that is what we are trying to do. So how to do it is pretty simple. So we'll import numpy as np. So we have OpenCV2, we have numpy. Now what we'll do is pretty simple. We'll read the image. So reading image is simple. So cv2.im read to read the image. Then what is the image that we are going to read? So the name of the image is called as i6.png. So i6.png is the name of the image that we are trying to read. So since I don't I've already done this many times, I don't want to show the image again. It will appear, but I want to do the kernel part. So what is the kernel that I am trying to do here is, every kernel is nothing but, it is pretty simple. So kernel is nothing but a set of ones. So it is like a matrix of ones that is available here. So your kernel can be 5x5 kernel, 10x10 kernel, 20x20 kernel. But here what we'll do is we'll create a 5x5 kernel. So what is 5x5 kernel here? 5 pixels. Height is 5 pixels, width is 5 pixels. So it is nothing here, it is a 2x2 kernel. 2 rows, 2 columns, 2x2. We'll first try to create a 5x5 kernel. So how to create ones is nothing but using the numpy library to create ones. So if you want to create ones, you need to use np.ones. Numpy.ones will create ones. But how many ones you want? We need 5 rows of ones and 5 columns of ones. So that is why you need 5, 5. Okay. So then you want that one to be a floating point or an integer value. If you want an integer value, you need to use np.uint. So what is uint? Unsigned integer of 8-bit. So what you are trying to do is, here you are trying to create a image, not an exact image. Since image is also a set of mathematical matrices, what we are trying to create is a 5x5 matrix. But how are we creating a 5x5 matrix is pretty important to understand. So what you are trying to do is, you are trying to create a 5x5 matrix, but that 5x5 matrix should be all ones. So that is why you have this numpy, which creates, which is a mathematical library in your Python programming language, which can create multi-dimensional numerical arrays, as well as it can be used for your multi-dimensional mathematical operations. So you can add 5, you can do your 5 plus 5 is equal to 10 or 10 plus 10 is equal to 20. But if you want to do matrix multiplication, matrix addition, you can't do directly using your Python, that is integers or floating point. What you need to do exactly is, you need to use this numpy to create this multi-dimensional arrays. So that is what you will do here. So how to do that is pretty simple. So after creating this mathematical array of 5x5, we'll try to print this one. So we'll print the kernel. So kernel is a variable which is a 5x5 array. So now we can see 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 5x5 matrix is being created now. So how will it look like? So I want to see how will it look like. So cv2.im show, I want to name it as kernel. So then I want to show the kernel. So how do I show the kernel? It is nothing but I will close this particular string. So then what I will do is I will mention the variable which I want to show. So if I want to see the kernel, so you can see here it is just a small 5x5. See, 5x5 will look that small. It is a black 5x5 like a data that is available, because I told you intensity of 1 is 0 is pitch black, 1 is also almost pitch black only. So that is what. So if I want to do 500 cross 500, If I want to create a kernel of 500 cross 500, how would it look like? So 500 cross 500 will look like this. It is a complete black one. But what is the whole point of using this kernel in erosion is pretty simple. So this kernel is called as a filter in erosion. So what we are trying to do is we are trying to move the kernel to the whole image. So that small 5 cross 5 will try to move through the whole image, and what it does is it is going to remove some particular dots or impurities, as well as it is going to erode some part of the image. So that is what it is going to do. So if I want to I want to perform that is nothing but erosion operation. So how will I perform erosion operation? So erosion can be done in a pretty simple way. You need to write a variable name. So what is the variable 9? So we need to use this simple variable called as erosion. So you can keep it as anything. It is a variable. Okay. So erosion is my variable. So cv2.erode is the function. So erode is the function. What I need to erode? I need to erode my image, that is img. So you can name it as any variable that you have read the image. So I need to remove this. So what am I using to erode? I am using this kernel. So I am using this kernel to erode. So that is what is my particular provision to do it. So if I want to use this particular provision to erode, so I am eroding this. But I need to see what I have eroded. So cv2.im show erosion is I need to name the window, right? So window is eroded image. So what is the image? Image is erosion because I have passed the particular kernel through this image, and the data is getting stored in this erosion. So that is the whole part. Now I need to check this thing. So you can see, I think you can see it. I think small part of the image is getting eroded. So you can, the hexagon was big, but when you compare it with the hexagon that is generated here, so it is quite small. So see, you can see this size difference. Since this is a 5 cross 5 kernel, it has eroded the whole like the background, or what you call it as the edges. So it has eroded the edges. Now the next thing what we'll do is we'll try to increase this kernel. Let us make it into a 10 cross 10 kernel. So we'll see more difference here. So if I want to make it as a 10 cross 10 kernel, see now still more data is getting eroded. So still more data you can see getting eroded. So what if I make my kernel very big? So if I make it to a 50 cross 50 kernel, I'll make it a very big kernel. What happens is it became completely black. So why did it become completely black? My kernel was such big that all the surrounding pixels were black, and there was a small change in intensity in the middle, so it removed. If the object that is there in this particular image, if the disturbance that is there in the particular image is like very large, then it needs a bigger kernel. If the disturbance is small, the kernel also needs to be at the same size of the disturbance so that it removes the particular thing. So if I make the kernel very big, it removes the entire disturbance. So that is what. It is like a filter. So 50 cross 50 is like 50 pixels by 50 pixels. So since this small hexagon is less than 50 pixels, so that is why it is not getting eroded. So that is the whole part here. So very important to understand what is the size of the pixels that you need to use for erosion. So this is all about erosion. So if I want to try it out on any other image, so let me try out in this A image what happens here. So since I'm trying out on A image, so it should get smaller, or what I can say is the A must be eroded right now. So this can be used for a color image also. It's not only for a black and white or a grayscale image. Let us try this. So it is a.png. So let us make it as a 5 cross 5 kernel itself and try what happens. So see here. So you can see the difference here. So A cross or the 5 cross 5 kernel is trying to remove the A. So A is getting very diminished, and you're just able to see a bleak image of A. So if I use a 10 cross 10, obviously I think 99% most of the A part will be removed, because the point or the kernel that I am choosing is bigger. So it will try to remove the entire S. That is why I am getting this whole just a blue or purple colored image. So that is how you can understand erosion. So erosion does not remove everything at once. It sees the kernel first. What is the size of the kernel and what is the size of the disturbance? So if the disturbance is large when compared to kernel size, then it will remove the edges. Only the edge pixels it is going to remove. If disturbance is like small and the kernel is large, it is going to remove the entire disturbance. So that is what is happening in this example of erosion. So the next operation that we are going to see is called as dilation. So what is dilation and how actually dilation is working is pretty simple. It is the opposite operation of erosion. So in erosion, what we saw, the pixels were getting removed. Here the pixels are getting added. So how it is happening is pretty simple. So when you have this pixel that is 255 or like dark, or if there is any change in the pixel, for example, here we have a pixel that is 255 and 255. So we'll consider 244. Okay, any large intensity or small intensity pixel. So here we have a pixel and here also we have a lot of information here. So the same kernel will go through this entire. The same 1, that is 1 cross 1 kernel will go through this entire image. But whenever it tries to find out a larger intensity values, so here if there are surrounding low intensities values like 1, 2 and 3, so what it is trying to do is, it is going to replace this low intensity value. So here we have some low intensity values, that is 3. So it is going to replace this low intensity values with high intensity values. So it is going to replace it with 255. So what it is trying to do is, it will try to go through this entire image, the same operation, like the same 1 cross 1 kernel is going to do, like going through the entire images. But whenever it is finding variation in the pixel, so if there are darker pixels and lighter pixels, what it used to do earlier is, it used to remove those high intensity pixels. So if you had 255 here, it used to remove this 255 and it used to replace it with like 3 or 4 or small intensity values. But what it is trying to do here is, it is even like replacing the normal values or the lower intensity values with higher intensity values because of the dilation concept. So what is dilation is, whenever I have a text that is very bleak. So if the text is very light, I have taken a photo of some like text or page, but the text I am not able to see because the image that I have taken is of lesser quality. So what I am trying to get is, I am trying to get a very small or bleak value of A. So I can show you the particular example. So if you have this particular A letter, so you can't see anything, right? It is difficult to see. So if I do dilation, the surrounding pixel will also be surrounded with this black pixel. So since the black pixel is a different intensity pixel when I compare it to the background, so the background also gets added to this particular pixel. So that is why it is getting embossed or it is getting dilated. So in dilation operation, what happens? The same thing, this 1, 1, 1 kernel, that is nothing but the kernel, is actually going through the entire image. But wherever it finds the different intensity pixel, so whenever it is finding, there is some value which has different intensity. Earlier in erosion, it used to remove those different intensity pixel and replace it with lower intensity of the background. Now it replaces the surrounding background pixels only with high intensity value, so that the text is getting embossed. So that is the total operation it is doing for dilation. So dilation is the reverse operation. So if I want to do the dilation operation, it is simple. So instead of using erode, we will use the dilate operation. So what it is trying to do is, I will rename this as dilate. So you can keep it as same, but for a good programmer, you need to put the correct variable name. So dilated image. So I can rename this as dilate. So what it is trying to do here is, it will emboss. See, A was visible normally, but it is embossing. Even the surrounding pixels which are pink in color is getting replaced by white. So how it is doing? It is passing the same 1 cross, like the 5 cross 5 or 10 cross 10 kernel here. So after passing it, what it is trying to do is, it is trying to see which is the surrounding pixel and which is the edge pixel of the particular letter. So where is the pixel intensity getting varied? At that point, what it is doing is, it is trying to even the background pixels, it is trying to add it into the variation or the change in intensity pixel. So the background is pink, but the variation or the disturbance is white. So it is even trying to make the background to white. So it is turning the color of the background into the color of the disturbance. So that is what it is doing. So this is the operation of your particular dilation. So we learned two things. One is dilation and one is erosion. So this was the basic tutorial on some morphological operations of image processing.